Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Before I start for this presentation, I would like to thank you for accepting our paper in BEEI journal. Let me introduce myself in the talk. My name is Eddy PN. I'm a graduate student from Computer Science Department, UPI University, and I'm lecturer from BEEI. Today, I would like to present about our research entitled IoT drone trajectory planning model with edge computing based on LoRa payload in rural areas with paper ID 8776. The author of our research are Eddy PN, Taufik Cakna, Imas Sugasi Sutanggang, and Irman Hermadi. A lot of those affiliation is from IDP University, Bogor, Indonesia. This is outline of my presentation. So I will start with the introduction, then move on to methodology, and then continue to result discussion, finally conclusion. The first part of my presentation begins the introduction. Our research is motivated by the implementation of precision agriculture or PA with using the drone in rural areas like tea plantation. According to Putri, rural areas have topographic characteristics with large areas such as those in agriculture or hilly areas, and the challenge is that communication infrastructure facilities are minimal. On the other hand, there is demand of drone to be smart in implementing PA in order to monitor the visibility of picking in large and hilly plantation areas. However, according to Agrawal and Kumar, IoT and drone have limited resources as mobile edge computing for the capabilities of the sensors, of the energy, computing power with and storage. Smart drone require edge computing that can help drones provide useful information according to PI needs. In this case, smart drones are able to classify drone image via camera sensor so that the position of the tea plantation area is suitable for picking. This classification information along with information from other drone sensor needs to be sent to the ground control station or GGS server to get monitoring result. This requires communication technology so that drone data reach GGS reliably. Therefore, LoRa technology is needed. It is known to be able to reach wide and appropriate communication in rural areas and drone trajectory to get better solution. From this, the following research question arise. Number one, how to identify IoT through metadata with LoRa precisely in rural areas of tea plantations, especially for the visibility of picking. Number two, how can drone computing become smart to classify the visibility of the picking tea and with a machine learning approach? Number three, monitoring a large rural area or in the tea plantation require time on human effort. Therefore, effective information is needed from the drone pilot needed by IT drone regulatory planning on LoRa network on the feasibility of tea plant picking to be formed. To provide a solution to this, we propose solution with the objective research are identifying pilot metadata from LoRa-based IoT drone sensor data with its computing to form uh, reference dataset for the picking needs. Number two, forming drone trajectory planning model from IoT drone pilot metadata information on monitoring the visibility uh, the plantation picking area. So we realized that not everyone knows and have been wondering about edge computing of drone with machine learning approach or IN classification of image, metadata pilot drone identification, and IoT drone trajectory planning in the plantation area. In relation to the solution offer, we have conducted a review investigation with previous research. You can see the comparison and the research gap. In the table, the first claim from our research is related to the formation of IT drone pilot metadata in rural areas. In our research, we produce the integrated integration of classified information from drone edge computing and other drone sensor information based on the LoRa protocol, successfully sending data via LoRa to GGS in rural areas. The second claim is related to IoT drone trajectory planning in rural areas, which result in the use of IoT drone trajectory in the smart agriculture application area for the feasibility of picking tea plantation areas, optimization of location information, shortest distance, throughput, and battery energy consumption. Now let's move to second part, which is about research method or methodology. And this research methodology, the states are based on the following research framework, starting with data acquisition or collection with drone, following by its computing data processing on drone, then data transformation via LoRa for delivery to GGS, and finally IoT drone trajectory planning. And this can be seen in the functional architecture of the drone and GCS communication network via LoRa. As is this of the process or function will be detailed according to the process method used. From first objective, I want to talk about IoT drone pilot metadata formation with its computing. The process of identifying metadata or integrating drone pilot data begins with data extraction in drone image processing according to the needs of the tea plantation before edge computing or image classification is carried out. The technology process uses computer vision technique in OpenMV to process image based on the GLI vegetation index of the leaves. Next stage, the edge computing use machine learning with a sequential IN model from the image captured by drone, and then converting H5 model to TensorFlow, TensorFlow Lite, and save the model to OpenMV memory. The drone pilot data integration process in the result and discussion chapter really describe the integration process for designing LoRa-based drone pilot metadata frame. And then from second objective, I want to talk down trajectory planning information process. And here we carry out the process according to this path trajectory planning diagram. This diagram start identifying feature information from telemetry data received by the GGS server from the drone. This process was conducted to monitor the visibility of tea picking, focusing on location data, drone flight paths, timestamps, throughput, edge computing result, picking visibility classification, and battery energy consumption. The steps in the part tuning on painting process include turning data pattern into part based on the characteristic of trajectory data, fitting trajectory data, and finally finding the best result that fit the needs and limitation using trajectory data. In the result and discussion start follows adapting for a classification model for picking the plans with drone its computing. You can see in the diagram. Let's focus for a classification model. Uh, the image classification model that determine of collecting the speech of data received by the drone. The stage which described as follow formation of data set with GLI formula. The level of greenness above uh, absent from the image was calculated in the value from -1 to 1 scale to a value range 0 to 1 with visualization in this figure. And next, data processing for the model, defining the training section was 75% equal to 138 and testing data to 25%, namely 46 data. And then in next step, the building of the machine learning model included implementing a sequential ion model using crash transformer module. This model consists of layer input data, 12 input layers, which contain feature information from the data set and one classification output layer. And based on confusion matrix, uh, the evolution of the classification model produced precision 63%, recall 1, F1 score 77%, and accuracy 82% based on the prediction result. Finally, the last process for designing LoRa this drone pilot metadata frame can see this side. The pilot included data from the OpenMV camera, which capture image of the plantation. The image was then processed using an algorithm for classification for visibility picking. The slide show the integration process with OpenMV data and onboard sensor. Finally, transform data by sending drone pilot data packet to GCS at a frequency 425 megahertz and size of 160 bytes each using LoRa base. The monitoring result in the telemetry data section of this table. So data processing result from drone computing to LoRa based GGS. Okay, let's turn to the next part about the monitoring with the IoT drone trajectory planning from second objective. The monitoring result received by GCS are telemetry data that can be seen in this front end video, which is real-time information transmitted by the drone to the GCS server via LoRa. And the focus is on the information on the status implementation image classification with IN in the result of the edge computing test from the OpenMV drone camera sensor and can be seen on this page during the drone flight. Based on the telemetry that in this GGS, the altitude trajectory can be formed based on the movement of the drone position in monitoring the key plantation regarding the visibility of the picking area. In this case, this discussion uh, of the drone trajectory is focused on location parameter, uh, battery energy consumption, and throughput. This graph shows the result of drone territory processing with location tracking parameter from the drone and battery energy consumption of drone. According Agrawal and Kumar argued that the planning method aim to optimize the path for processing data, thereby generating optimum result. In this scenario, our research design IoT drone trajectory planning with the following formula uh, to achieve the shortest distance in this one with simulated annealing algorithm. We propose optimize shortest distance. Number two, minimum battery energy consumption, and number three, maximum data throughput. Based on testing with drone flight in the tea plantation, the analysis of the result of drone trajectory planning on the success of sending packet data, throughput, energy consumption, drop flight time, altitude, and prediction of classification result can be seen in this table. The transmission of metadata successful send completely reaching an average of 97%. And the next, this graph show the result of analysis of throughput and battery energy consumption by the turn pilot module. This is a claim achievement second indicator. Uh, from this, at an altitude 17.88 meters, is drone flight produce an average throughput of 16.95 bits per second, with its packet size is 160 bytes base LoRa, and consume 0.467 watt hour of battery energy pellet drone module. The location trajectory drone was proposed to optimize the shortest distance using the TSP method with simulated annealing algorithm. And figure A shows you the position of the tracking drone starting from the point of the garden position that will be being picking as the basis of sending a new graph of the shortest distance with the traveling solution problem approach with the simulated annealing algorithm shown in picture B. In conclusion, I'd like to end by emphasizing the main point. The first one, implementing smart drone in PA in rural tea plantation area necessitated a mechanism for developing a drone metadata, which consists of a data integration process with its computing result from the drone image classification and on board drone sensor data. This second one, the sequential ANN from crash TensorFlow model was successfully applied based on GLI calculation dataset on each image pixel, which included 12 dataset input layer and activation function with a rectified linear unit or ReLU and one classification layer in the drone image classification process to determine the suitability of the plantation picking areas. LoRa-based drone pilot data packet will successfully sent to GGS. On average, 97% contain identification information collected by the sensor of the drone, such as flight time, location, calibration, pilot drone battery energy, garden profile, temperature, and humidity. And uh, uh, the last conclusion, the IoT drone trajectories in rural tea plantation areas that consider food, successful data triangulation, identification of locations suitable for drone picking and tracking, and battery energy consumption. The TSP approach with a small data analysis algorithm utilize the location trajectory result to determine the shortest distance from the position of the pickup, producing a new graph. The resulting drone trajectory show maximum data throughput and minimum battery energy consumption of the drone pilot. Uh, Thank you for your attention.